Welcome to the 1.3 release note of Dyna, the fourth major release since March 1998. In this release, the first new facility is the Monte Carlo solver. You essentially applied an input distribution to a parameter or many parameter, and you obtain by running a multiple series of a steady state solution an output distribution of the target variable. In this example, we're going to apply an input distribution to the cell amperage with a mean of 300 kiloamps, the standard deviation of 2 kiloamps. Going to run 2000 cycles to obtain the corresponding output distribution of the anode cathode distance. So you solve in sequence a 2000 solution. Here is the first solution where the input was picked at random for 297 kiloamps and you obtain 6 centimeter of ACD. Here at the end of the 2000 cycle, you get the green curve is the target input distribution. The histogram is the real obtained distribution after 2000 cycle for the input variable. And this is the corresponding output distribution for the anode cathode distance. From that facility, we can assess the risk associated with the inaccuracy of predicting some input parameter to the model. Next addition is the current curtailment facility. Here in this example, starting at 300 kiloamps, we drop the amperage after an hour by 30 kiloamps, run at 270 kiloamps for an hour, and ramp back up the amperage to the initial 200 kiloamps in 30 minutes. This curve is the target amperage, and we can add the real amperage was obtained. Them on the same scale. So this is the actual simulation of the amperage considering the noise to the rectifier. This was obtained by programming the current curtailment panel. You can see that we have obtained this by essentially two entry to the scheduled current curtailment facility. First is a drop of 30 kiloamps in one-time step after 60 minutes of simulation. The second is the increase with a ramp of 30 minutes after 2 hours of simulation. Third addition is the anode change target resistance setup. Here we program at the time of the anode change a change of the resistance target for an amount of time, and then a ramp back to the initial value of target resistance of the cell in order to maintain the anode cathode distance constant, considering the fact that the current densities increase after a new anode is set. We can here add the actual cell to the resistance obtained. Again, we can put that on the same axis. So we can see the anode motion that we are ordered by the controller. resistance into the range, the target resistance. Next addition is instability treatment. Here we first trigger the noise simulation. And so this solution here, we are getting the noise, and we are operating here a side broken pot, and there's a anode effect occurring on average every day, and every feeding cycle you getting closer to anode effect, and by doing so you are squeezing the ACD and creating more noise. So this is an obtained noise, and we can add as a second graph the target pseudo resistance to see that we were actually doing some treatment, instability treatment at many places when the noise was getting too high. This was programmed in the new instability treatment panel. Essentially set an instability treatment for up to 4 levels with a trigger to start that instability treatment, and a trigger level to either increase to the next level or decrease to the base level. There's also the addition of the ratio control facility. In this example, the cell is well under control at 8.5% excess ALF3, running at 300 kiloamps, but after a day of operation, the amperage is increased to 305. This creates a sudden melt of the ledge and the dissolution of the excess ALF3, and doing some work to the controller that must change the amount of excess ALF3 feed to the cell to go back to target 8.5%. You can see here the graph of the increase of amperage. And you can see the panel where this was programmed. Essentially, we're setting up a schedule of bat sampling, and then a logic to change the amount of ALS3 feed to the cell based on the offset between the actual value of the excess ALF3 and the target value. You can see here in the event list that there's a new feature also in this version. What actually happened, we were feeding periodically 6 kilograms, and then at 8 hours in the simulation, we took a bat sample. A day later, we got the analysis of that sample that was right on target. So we have not changed the adjustment of the ALF3, but in the meantime, the cell amperage was increased by 5 kiloamps at exactly after a day of simulation. As a result, the next sample was too low, 8.37, and triggering an increase in the adjustment of the 3 to 6.3 kilogram, and so on until we reach up to 9 point something, and then starting to go back down essentially creating a wave of adjustment. Next, last thing that we want to present to you is a new panel for matte additive, essentially to say that we are now able to add NAF and the 3-carbonate form of additive. So this concludes the 1.3 release note of Dyna. Thank you for your attention.